All right, let's do resistance. So resistance is the next topic in this unit after current. Current describes what is happening, which is charge flowing through a conductor, and resistance goes into a little bit of how much that's happening or why it's happening. So the resistance is the property of electrical conductors that describes how much it resists or impedes the current. Sometimes resistance is also called impedance, but that word isn't used very often anymore. But if you're ever reading something and it says impedance, that means the same thing as resistance. The smaller the resistance, the more easily current can flow. And generally speaking, more current will flow. And we will quantify this in the next topic. Almost all conductors resist current flow by some amount. And we say almost because there is something in physics called a superconductor. And I'll put some sort of bonus material up if you want to learn more about that. But that's not really a required topic in this course. It's something that only happens when certain special materials get very, very cold. Try to think about some things that might affect how much a conductor resists current. So if I have a conductor, which is usually a wire, what are some things you might want to know about that wire in order to guess the resistance? Well, I want to know what it's made of, and then I might want to know the dimensions, such as the length and the width of the wire. And if we know these three things, we pretty much know exactly everything that goes on in that wire. Another one is temperature. But it turns out that only these first three things are going to be things that we specifically calculate using the formulas. So this what it's made of factor goes with this letter, this funny looking P thing, which is the Greek letter rho. And this is resistivity. I don't think I have one printed out, but there is a table of resistivities for different materials on the reference table. So there's a number for each material. And the units, I believe, are ohm meters. We'll come back to this. L is just the length of the wire, the conductor, in meters. And this A basically goes with the width. It's the cross-sectional area in square meters. So this will be a really small number. Because if we picture a little wire, this would be the length. If you were to chop up that wire and measure the area of this circle, That's the cross-sectional area. And then the actual material that the wire is made of determines what the rho is. And that basically describes, in that material, how much stuff is there in the way, making it more difficult for charge to flow. Okay. So, the formula is resistance equals rho times L over A. So the resistivity times the length divided by the area. And the units of resistance are ohms, which are related to coulombs. Let's see. An ohm is a volt per amp. Volts, you might remember, describe potential. Amps describe current. Both of these are related to coulombs. But anytime you have a number that's resistance, its units are ohms. Okay. So, for example, you might have a particular conductor that has a resistance of 3 ohms. A resistor is a conductor that's built to have a specific amount of resistance. In a circuit diagram, a little zigzag like that represents a resistor. And a resistor usually has a lot more resistance than a plain metal wire. So a plain metal wire that's like made of copper that you would use to hook things up usually has a pretty small resistance. And a resistor you could picture as being a super thin wire, sort of scrunched up, that's why it looks like this, or coiled up inside of a little object. And that has a lot more resistance than like a plain wire because it's specifically built to have a certain amount specifically of resistance. This is what the symbol looks like. The actual object is really small and it looks like this little kind of peanut shaped thing. And it will have colored stripes on it, and the colors of the stripes are a code that tells you how much resistance it has. So when we get into circuits, we'll explore that a little bit more. The resistance of a material also depends on temperature. If it has a higher temperature, that means it has higher resistance, and if it has a lower temperature, that means it has lower resistance. You can kind of picture the little particles in the wire. If these are moving around more, then it's harder for the electrons to get through. Right? When you walk through the hallways between classes, everybody's running around, everybody's going crazy. When that's the case, it's much harder to get through than if everybody was just like walking very slowly or standing quietly and you could just get through. So when the particles of the material are moving around faster, it's harder for the current to get through. We have a higher resistance. Okay. So let's do some examples. This formula is not too bad, but as you've probably kind of gotten used to with the Coulomb's law stuff and the electrostatics equations, it can be a little bit tricky when the numbers are in scientific notation. Okay, so I pulled up my reference table. A gold wire has a resistance of 0.012 ohms. This is going to be R. And a cross-sectional area of 4.0 times 10 to the negative 6 square meters. This is A. Like I said, A tends to be small numbers because a square meter is a lot of area, and we're talking about this area of the tiny little circle on the end of the wire. We're looking for L. And then there's one other variable in our equation, this rho. And because it says gold, I can look at the table on page 4 of the reference table, and it tells me that this rho is 2.44 times 10 to the negative 8 ohm meters. So I'm going to use R is 0.012 ohms. Area is 4.0 times 6 meters squared. I'm going to plug in all these numbers. Since I already wrote the units over here, it's okay to just write the numbers. Over here's my equation with the numbers plugged in. And now I will calculate it out. So I'm going to divide these two numbers on the calculator. (2.44 e key negative 8 divided by 4.0 e negative 6 is 0.0061. So I have 0.012 equals 0.0061 times L. So then I'm going to divide both sides by this 0.0061. And I have 0.12 divided by 0.0061 comes out to be, I'll round this up to 2.0 meters. But if you wrote 1.97, that would be fine. But since I'm given two significant digits in the question, it's fine to just round to that many. Okay. Why don't we have you guys try the next one and just write your answer in the assignment submission box. So a copper wire is 12 meters long and it has a resistance of 1.5 ohms. What is its cross-sectional area? So you're going to be solving for A, and because this has a copper wire, you're going to use the resistivity for copper that it has on the reference table. If you have one printed out, great. It's on the same page that we have our electrical equations with. If you don't have one printed out, you can just Google physics reference table. It's pretty easy to find. And I want to force you to check and find this number in the table. But it's going to be a small number like this resistivity was. Because copper allows a lot of current to flow. And that means that its resistivity is a pretty small number. Okay, good luck everybody. Keep an eye out for the next resistance activity, which is going to be a video of a demo where we represent chart electric current with air current.